right, so welcome to Chapter 7. This is really about scatterplots and how we can kind of look at scatterplots, two variable data, describe them, and kind of talk about the different relationships between the variables that we are investigating. All right, so we're going to look at a scatterplot first, and we're just going to kind of go over the basics. We talked about this a little bit when we did when you did the Monopoly lab, right? That's essentially a pretty basic example of simply putting coordinates on the coordinate plane. And so that's something we've done 100 times over. And so here we have all the sandwiches in the Burger King menu, and we've written down two things about each sandwich, right? So in terms of a scatter plot, what are the relevant pieces? Well, you got your title at the top, you've got your x-axis label, you've got your y-axis label, and of course you've got all the dots in the middle. Each individual point is a sandwich. We know two things about that sandwich. We know its protein value and we know its fat value, right? We know those different contents. So it's a traditional XY coordinate plane. There's really nothing special about that. We typically call the x-axis. Sometimes you hear it referenced as an independent variable. We have different definitions for independence and dependence. So we're going to call the x-axis the explanatory variable. We're going to call the y-axis the response variable. And what we tend to try to do is we try to show an explanatory response relationship, right? That one don't say cause, because that's really, really inappropriate. Association is not causation. That's in your chapter. You definitely check that part out. We're simply showing what two things are doing at the same time, right? For example, the protein content doesn't really cause the fat content to be high or low, but they do tend to go together. And so a lot of the time, like with a Monopoly, because we were manipulating the spaces from Go, then the reaction to that was, well, as I went around, I saw that the protein content, the price of the property would change based on where I was. So we thought that, well, we're going to put the explanatory variable as the number of spaces from Go, and what responds to that is the price. And we're going to do that the same way here. There is no requirement for an explanatory response relationship to make a scatter plot. For example, the protein content and the fat content doesn't necessarily have that clear-cut relationship that protein impacts fat, right? Or fat impacts protein. You kind of could do it either way. I could have put the fat content on the protein or on the x-axis, and I could have put protein on the y-axis. And I would have still gotten a fairly good explanation and response. It wouldn't have been very much different than we're looking at now. Sometimes it does seem to be obvious, and sometimes it doesn't, and that's okay. We're not really trying to show that. We can see a couple things when we look at scatter plots, right? And this is the key element. Last time when I said describe the distribution, you guys went in and you made a graph and you talked about shape, center, and spread. But this example, I can't quite do that, at least not as clear as I could last time. We're going to be doing this one, strength, direction, and form. Okay? The easiest of all those things is form, right? Is it linear? Is it straight? Or has it got a bend to? Is it curved? Right? In this example, we can clearly see that you have this big pattern here. It's a very linear pattern. So that's form. Direction, also really easy to do. Do we have a positive association or is it negative? In this example, it is very clearly positive, right? It goes from the bottom left up to the top right. If it had been negative relationship, it would have kind of gone down as you went along the x-axis. Okay, and then we have the last one, which is strength. Strength is the most complicated. It's very difficult for us to use our eyes to judge strength. By basic definition, strength is how close are the points to a line. The good news is that I don't have to rely on my eyes to make that judgment call. We are going to learn how to do this in the calculator and allow that number we get out, which is called the correlation coefficient, or R, to tell me how strong something is. Okay, it also tells me, the sign of R tells me the direction. So when I do this in the calculator, I'm going to get that value and I'm going to be able to talk about how strong it is. Now, if I'm looking at this here, when I'm looking at this particular graph, I can see that it is definitely a fairly strong relationship. not super strong, right? But it's definitely more definitely defined as a linear pattern. It's not curved. I don't have this oval shape that's kind of rounded. The closer to a big square of dots, or maybe even a circle of dots, the closer to zero I get, the closer to no correlation or no relationship at all. Here it's pretty clearly defined. And I would say this is definitely medium strong to strong relationship. And we'll define a few of those things as we go along. Okay, the direction, here's an example of a positive relationship where you can see in the purple, or the dark blue. And then you have the gold color, which is a negative relationship. Remember, positive means the two variables are increasing at the same time. A negative relationship means the two variables are inversely related. One goes up, the other goes down. Not really going to take a lot of time to talk about this one. This is a pretty straightforward part. The next one is form. We're going to look at a few examples here. Here we can see two definite linear forms at the top two, right? You can see up in the top two values, definitely a positive linear form and a negative linear form. Here we have almost no form at all. This is almost a zero correlation. I don't have any sense of direction. Is it leaning to the right, to the left? It's not curved, but there's also no form at all, right? So not linear. This is definitely non-linear. It is a strongly correlated value, but it's not linear correlation, and we are studying linear correlation. So this is definitely quadratic. If you really want to do this right way, you would do a quadratic regression, right? We aren't studying that, right? The only thing you would say for this is that this is not linear, then my methods aren't sufficient to describe this, and you move on, right? So we're not going to deal with this kind of thing, right? We just want to know, is it linear or not? Pretty straightforward, okay? The last one is strength or correlation. This is the one that requires the most amount of kind of consideration. I need to think about this. The good thing is that your calculator is going to do it. Here you can see a correlation of 0, which doesn't have any kind of form to it at all. It's beginning to get a slight lean to the left in this one, and correlation of 0.5, right? I kind of think of, if I have like an oval, a football kind of shape to it, that's that close to that 0.5 range. And then the closer it gets to a line, the stronger it's going to get. And remember, perfectly strong positive is going to be a +1. A perfectly strong negative is going to be all in one line, but it'll lean to the left, right? Have a negative slope. And you can see that as the correlation gets stronger as you go along these. Remember, positive and negative isn't about strength. Positive and negative is about directions. They're leaning to the right, to the left. A positive slope or a negative slope. How close the dots are to a line, that's the value. The closer to 1 or -1 you are, the stronger the relationship. The closer to 0 you are, the weaker the relationship. As a guideline, typically you can talk about things, if it's 0.33 or below, you can talk about that as a weaker relationship. Between 0.33 and say 0.7, then you've got, or 0.67, you've got that moderate relationship in the middle, and then of course towards the end, 0.7 and up, you tend to talk about your stronger relationships. There's a lot of things here you can talk about. It's moderately strong, it's on the weaker side of moderate, it's those kinds of things. You can definitely qualify those as you describe them. Lines of best fit. The best way to kind of take this, this is the method that we talked about in the scatter plot. We're not really going to do this, but let me just talk to you about that for a minute. In your calculators, you're going to find lin reg. All right, you can go in, if you press stat, right, 8, it's going to bring up lin reg. And if you want a kind of a written out definition, if you'll go to this week's overview, I wrote down all the directions for this specifically. So I'm just going to reference that. I'm going to talk about it here. You're going to put in L1, you're going to put your X's in, and L2, you're going to put your Y's in. You're going to go, after that, you're going to go stat right 8, and then bring up lin reg. You're going to make sure that the X and the Y list are correct. A pro tip here is you want to add in Y1 for the regression EQ, because I'd like to graph my scatter plot along with my line of best fit. And this line of best fit is called the least squares regression line. It is one of the most accurate regression lines that we can make. And so we were going to reference that. We're just going to call it LSRL. And so when I do that, if I press vars, right, enter, enter, that's on the review, it's on the overview, you can check it out. I'm going to bring up y1 in place of that. I'm going to go down. I'm going to hit calculate at this point. When I do that, it's going to return me 4 values, a, b, r, and r squared. Okay. If you don't see this, you can go to your mode, go down to stat diagnostic and turn it on. Here again, that's on the overview. And make sure this way, when you do linreg, you'll get all 4 values. If that's off, you won't get r and r squared. And if this is the first time you've ever done it, you probably won't get it. So go do that first. All right. A and b is going to be my y-intercept and my slope of my line. R is the correlation coefficient. This is how we define strength. If it's positive, it's a positive association. If it's a negative association. The closer to 1 or -1 we have, the stronger the relationship is. R squared, I'm going to kind of leave that discussion for another day. That's called the coefficient of determination, but we'll talk about that in Chapter 8 a little bit more specifically. So let's just kind of leave it at that. When you do that, you can write down your line of best fit. It's going to give you the form y equals a plus bx. A is your y-intercept and b is your slope. Plug those values in and write that down for your y hat equation. We use the hat because it's an estimated y value. The x is definitely an x value, but when we plug numbers in, like you did for the Monopoly board, you got an estimated value for that 50th space, right? And that hat, that little point on the top, is considered to be our estimated value. Specifically, talking about predicting, there are 2 ways we can predict, right? We can use that line of best fit to make predictions, and when we predict within our data set, we call that interpolation. That means that I've got data, I've got evidence, I know exactly how that should play out, and so I've done that, I can predict within that. If I had predicted for a space like number 7 on the Monopoly board, I could know pretty well how that's going to go, because I have data before, I've got data after that, and so I've got evidence to say that that's the pattern right in there. However, if I try to predict outside of the range, we call this extrapolation. Predicting for the space of 50, I had to assume something. I had to assume that the pattern of those properties kept going even after my data stopped. A good example of this is if I were to record the heights of an individual from the time that they were born all the way to the age of 16. And then I would extrapolate beyond the age of 16 and try to predict how tall they're going to be at 30 or 40 or even 50. I'm going to get ridiculous answers because at that point you're growing, right? And you're continuing to grow, but we know that you don't continue to grow for your lifetime. You stop growing at a certain point. And by the time you're 20, 30, 40, or 50, you've definitely stopped growing. And so that growth pattern tapers off, right? It flattens out eventually. And so I would be extrapolating with data that doesn't do that. So when you extrapolate, you can't really trust that data. It is something that you don't ever try to trust. You can do it. It is an estimated value. It is not trustworthy to kind of go with. And that's essentially Chapter 7. When you look at Chapter 7, make sure that your part where we talked about correlation is not causation, right? When we talk about things that happen at the same time, it is not the reason that it's not the cause and effect relationship we're discussing, right? So if you haven't read your chapter, definitely highly recommend you do that. It's not a very long chapter. Make sure that you know how to make a scatter plot, read a scatter plot, and kind of go through that. I did hit talking about how to make a scatter plot in the overview for this week. It's also in your book. There's 2 different TI tips you want to make sure to pay attention to: how to graph your scatter plot and how to do linreg. Okay? I hope this helps. If you had any questions, please let me know, and I will answer those as best as I can. See you next time.